Today we're going to talk about the existence of square roots. Let's have a quick recap of where we were in the last lesson. Recall that a quadruple is said to be a complete ordered field if the following 14 axioms hold. The first 10 explain that we have a field. That is, we need properties that say that the sum and product of the elements are back in the set. We have other properties about addition, multiplication, and then finally we have a distributive property that explains how addition and multiplication are related. Next, we need three properties to explain the idea of being ordered. The most important of these is probably the trichotomy property. That is, given an element x, either x is 0, x is positive, or x is negative. And then finally, we have a property that explains that our field is complete. It's also called the least upper bound property. Given any non-empty subset A of our set F that has an upper bound, it must have a least upper bound. Using this, we'll construct the real numbers as a complete ordered field by looking at properties of the rational numbers. More generally, say that we have any ordered field. We'll say that a subset of this ordered field F is a Dedicant cut if it satisfies the following four properties. First, it must be non-empty and proper. Second, it must be closed downwards. And third, it must have no greatest element. The collection of all such Dedicant cuts we'll call the collection of real numbers. That is, we're going to identify a Dedicant cut as, simply put, a real number. Eventually, we're going to prove that the collection of real numbers forms a field that is ordered and complete. The hard part will be defining addition, multiplication, and an ordering. Let's do that here. Say that we're given two Dedicant cuts, capital A and capital B. First, we can define their sum and negation as follows. Next, we'll define an ordering by saying that our capital A is less than capital B whenever B minus A contains square bracket 0. Square bracket 0 in this case are just all of the negative elements. Third, we'll define the product and inverse as follows, but first we only define these for positive sets A and B. That is A and B that are greater than our square bracket 0. We'll then extend these to all of the other cases by essentially using the trichotomy law. With these definitions, we can actually look at the following examples. Let's let capital A be our square bracket R, that is all of the numbers in F that are to the left of R, and let's let capital B be square bracket S, that is all of the numbers in F that are to the left of S. These are both examples of Dedicant cuts, where the sum, A plus B, are just all of the elements to the left of R plus S. The negation, negative B, are just the set of all the elements to the left of negative S. We'll say that capital A is less than capital B if and only if R is less than S. A times B are just the elements to the left of R times S. And B inverse is just the set of elements to the left of S inverse, whenever S does not equal to 0. Using this property and the previous definitions, we actually see that the collection of Dedicant cuts does form a complete ordered field. When F is equal to Q, then this collection, of course, we call the real numbers, and this is our example of a complete ordered field, in which the rational numbers Q forms a subfield. Now, in all of this highly theoretical way of defining the real numbers, we haven't said at all of how to actually compute real numbers. Let's talk about that today. We'll discuss a specific example by talking about how to compute square roots of numbers. Let's give an application of what we've defined so far. Let's fix a number p that is greater than or equal to 1 and consider the following set. This will be the set of elements such that either it is positive, and t squared is less than or equal to p. This set is non-empty and it has an upper bound. Let's call that b. All upper bounds b satisfy b squared is greater than or equal to p. Let's assume for the moment that f is complete, and let's let s be the supremum of a. Then s squared equals p. In particular, this proposition shows that the square root of a number d for any d positive exists as long as f is complete. Here's the reason why. Let's consider three cases. First, let's say that our capital D is greater than or equal to 1. In this case, we'll just use the proposition by setting p is equal to d, and we realize that our square root is simply the supremum of this set. Next, let's say that d is greater than 0, but it's less than or equal to 1. Now we can consider p to be the reciprocal of d, so that p is greater than or equal to 1. Again, we'll use the proposition up above, and now we'll see that our square root of d can be written as the square root of p divided by p. Finally, when d is equal to 0, we'll just define its square root to be 0. Let's try to prove this proposition. We'll start by showing the very first statement. We need to show that we do have an upper bound for this set, and we need to show that this set is non-empty. Well, the element t is equal to 1 is an element of this set, because if I take a look at t is equal to 1 and square it, then t squared is less than or equal to p. We also claim that p is an upper bound for a. Indeed, because p is greater than 1, p squared is greater than p. So using this, we can actually see that every element t from our set A has to be less than or equal to p. Let's show the second statement too, by discussing what happens for any upper bound. To this effect, let's let b be an upper bound for a. We're going to show that b squared is greater than or equal to p. In fact, we'll do this by contradiction. Let's assume that we do have an upper bound, b, that satisfies b squared is less than p. Then let's define this new element t to be p times b plus p divided by b plus p. We'll prove a couple of facts here. First, t must be an element of a. Here's the reason why. First, we can prove that b times b plus p is positive, and b plus p is also positive. That means then the ratio, what we're calling here t, is also positive. Similarly, because p is greater than 1 and p minus b squared is positive, we can also see by some algebra that p minus t squared is positive, showing that t squared is less than p. This means that t is positive and t squared is less than p, so we conclude that t is an element of a. Next, we're going to show that our t is greater than b. This is a matter of realizing that t minus b we can express as p minus b squared, which is positive, divided by p plus b, which is also positive. Since the product of two positive numbers is positive, we see that t minus b must also be positive. Hence, t is indeed greater than b. Now we see that t is an element of a, but this means, because we have an upper bound, that t must be less than or equal to b. But the second statement says that t is greater than b, which yields a contradiction. That means that our original assumption, b squared is less than p, must have been false. So for any upper bound b, we must have b squared is greater than or equal to p. Let's now show the third statement about our upper bound. Let's say that a is non-empty. Since we know that a is non-empty, and we're assuming that f is complete, we see that the least upper bound, s, must exist. We're going to prove that s squared equals p. Since s is an upper bound, we've just seen that s squared must be greater than or equal to p. Now, let's choose any positive element epsilon. Since s is positive, and we know that 1 is an element of a, we must conclude that s is greater than or equal to 1. Let's denote epsilon prime as epsilon divided by 2s. Once we do this, then we realize that we can find a t sub epsilon such that s is less than t sub epsilon plus epsilon prime. Putting this together, we now see that s squared must be t sub epsilon squared plus the product you see on your screen. This is just because we have the difference of squares. We can bound this above because t is less than s for all t in our set A. Next, remember that s is less than t sub epsilon plus epsilon prime. Now we use our definition of epsilon prime and write this in terms of epsilon. But finally, recall that inside of A, t squared is less than or equal to p. That is our definition of capital A. So we've shown now that s squared is less than p plus epsilon for any positive element epsilon. This means that s squared must be less than or equal to p. But since we've seen that s squared is greater than or equal to p, we put this together to realize that s squared must be equal to p. Now let's end by discussing what happens if we actually wanted to find specific numerical values. The proposition just shows that our least upper bound for this set must be the square root of p whenever p is greater than or equal to 1. But how do we actually compute the square root? Let's give two different methods to do this. First, let's define the idea of an increasing sequence. We'll define a sequence t sub 0, t sub 1, and so forth recursively as follows. Let's start with t sub 0 equals 1, and let's define t sub n plus 1 as p times tn plus p divided by tn plus p. Hopefully this looks familiar from the proof that we just discussed. One can prove that we have an increasing sequence that starts at 1 and increases up until t sub n squared is less than or equal to p. And in fact, each t sub n squared is as close to p as we wish it to be. We'll prove this in a later lesson. To this effect, we will write t sub n approaches s, or we'll write the limit as n increases without bound of t sub n equals s, where s, of course, is our least upper bound, in this case, the square root of p. Similarly, we can construct a decreasing sequence. That is, let's define a sequence b sub 0, b sub 1, and so forth recursively as follows. B sub 0 equals p, and b sub n plus 1 is 1/2 b sub n plus p over b sub n. In this case, we have a decreasing sequence that starts at p and gets smaller and smaller, but each term b sub n satisfies b sub n squared is greater than or equal to p. And just like before, b sub n squared is as close to p as we wish it to be. Again, we'll prove this later. We'll say that b sub n approaches s, or we'll say that the limit as n increases without bound of b sub n equals s, where of course s is the square root of p. We'll introduce a lot more of this notation later, but for now we're just discussing some ideas. Here are some examples to explain numerically how this will play out for some very specific cases. On the left, you'll see p is equal to 2. Here, we'll start at t sub 0 equals 1 and b sub 0 equals p. In this case, p is equal to 2. Recall that t sub n we define recursively, as well as b sub n we define recursively. You can stare on the left-hand side at the column involving the t sub n's. Notice how it starts at 1.0, it goes to 1.3, and it increases steadily until we reach around 1.414. Of course, this is exactly what we expect as the square root of 2. On the right, you see here you have the b sub n's. We start at b sub 0 equals 2.0. We then decrease to b sub 1 equals 1.5. And we steadily decrease without the sequence until we get to 1.414, again the square root of 2. You see the same concept happens on the right-hand side when p is equal to 3. We start at t sub n equals 1. we also start at b sub 0 equals p, in this case p is equal to 3, and for the t sub n's we increase from 1.0 to 1.73. On the right we decrease starting at 3.0 and decreasing down to 1.73. In both cases we have sequences where we have a very good approximation for the square root of p. The t sub n's increase starting at 1, and the b sub n's decrease starting at p. But why can we do this? Why is there a sequence of rational numbers that approximates the square root of p? And can we do this with other real numbers s? We'll come back and we'll discuss this in a later lesson. Thanks for watching.